Obviously, we're very, very fortunate this Monday to have the speaker today, Claudia Perlich. She is very well known in the data science community in predictive modeling. She is very well known both in the academic community in terms of research and so on, but also as a speaker, as a mentor. So looking forward to her seminar today. She started her career at the IBM Watson Research Center, obviously very well known in the AI community, and she is an adjunct professor at the NYU School of Business, Stanford School of Business. She's also advisor for a couple of companies. Dstillery is one of them. And as I said, she's extremely well known in the field of data science and predictive modeling. One of the papers I've sort of this thing, look at the Google Scholar for our speakers, and one of the most cited paper is with bankruptcy and how you can actually predict that in data science. It's kind of interesting angle to that. So without further ado, thank you very much for being with us.
Thank you very much. So after the extensive introduction, I'll probably then just kind of skip mine because I was planning on telling you a little bit of my background from a PhD in a business school, which was an odd place to do machine learning back before 2000, and then going into IBM Watson, working on a couple of projects there, and a lot of my early publication come from kind of applying predictive modeling and machine learning to various challenges internally to IBM. And then after that, I went into advertising, and not because I particularly cared about advertising, but because that's just kind of the playground for data scientists, because you have an incredible amount of data, and the sky is the limit in terms of what you can do. And so after about 8 years of advertising, I grew a little bit too cynical about it and decided to instead join a hedge fund. Now, most of what I'm going to talk about is going to be on applications in the advertising space, because this is really where most of my experience is. And then towards the end, I have a couple of other examples that I think are interesting. So let's get right into it. I mean, we all see ads all day long, and we wish to pretend that we don't really see them, but they're pretty much everywhere, just kind of highlighting a few of them. And I'm not sure to what extent you're aware how kind of modern advertising works and what's the machinery behind it, especially in the case of display advertising. So let's take a quick tour into the advertising technology, shall we? So this is my mom. That actually is my mom. And she is one of the at least 200 million people who hasn't quite figured out yet how to delete third-party cookies. Which pretty much means that there are a lot of companies like Dstillery and many other ones you've never heard of that are kind of tracking her activity level on to some degree. So if she goes and reads the New York Times, say, there might be a slot available for a display ad like you saw earlier. What now happens that a large percentage of these opportunities are sold through what's called an ad exchange. This technology started around like 2010, give or take, where you now have real-time auctions where opportunities to show an ad are sold. And this is how the company I worked for, Dstillery, was kind of getting this information and is involved. So Dstillery was receiving between 15, and now it depends on how you double count, to 100 billion bid requests every day, at which point they can decide whether or not to submit a bid on behalf of one of the clients that we work for. I'll talk about the business model in a moment. Basically, you have 100 milliseconds time to submit a bid, because all of this happens while the page is loading. Now, if you win, you get to select the bid that goes there with some rules and restrictions around it. So then we get to show the ad in that slot. So what is the kind of business that Dstillery is in? We're obviously not advertising for ourselves, but we work for clients, for agencies, or for brands directly. So for instance, we might be working for a car manufacturer. And the thing that they care about, obviously, is that the person then shows some interest in the car. Now, typically, it's difficult to figure out whether they bought a car, and buying a car takes a long time. So typically, we are tracking some kind of action that we all agree we count as what's called a conversion. That could, for instance, be, does the person go to the website? Do they schedule a test drive? Do they kind of assemble a car? Or whatever it is that you can do online after having seen the ad. Typically, with some time window, say 7 days after seeing the ad, that would then be called a conversion. Obviously, it's not me making 50 billion decisions a day. This is where the topic of your seminar is. This is all about machine learning and full automation of all kinds of decisioning in that process. All right, so let's look at an example here. We'll get to cars in a moment, but let's assume Azure, Microsoft Azure. It's a machine learning platform and cloud provider. Where should my machine try to place these ads? Who should I try to show them to? It's all about what is the objective that I'm giving to kind of the AI to optimize towards. And so, for instance, one of the things is that Microsoft Azure is interested. Do they then sign up for a trial, or do they just go to the Azure homepage? So this is kind of the obvious application for machine learning. If I'm being measured on whether people, after seeing the Microsoft Azure ad, go to the Microsoft Azure homepage, then clearly I will build technology that predicts who goes to that website. So this is classic application of kind of a supervised learning where you're trying to build models that can predict who will go to the Azure website. So it's not just to the website, it's like whatever metric the client is interested in, whether these are clicks, or downloading, or signing up, or whatever. Like any metric the client is interested in, ultimately, I will build a model to predict, and I will use that model to then target specifically those people who have a very high likelihood to take that action that I'm interested in. We're kind of clear on how this works, principle? So this is the goal. Now let's actually come clean about the data. This is what it looks like. So basically, just by the virtue of being a member in this advertising space, Dstillery has access to all of the activities that are flowing through the advertising space. So every time we get a bid request, we are told that a machine is right now looking at a certain website and that it's coming from a certain IP address. So you have, by device, these histories of activities. And then you can connect devices based on them showing up at the same Wi-Fi, for instance, in the evening. So there's a very good chance that the device is, that two devices, my phone and my laptop, are owned by me because they constantly show up together on various Wi-Fis and specifically on kind of small Wi-Fis with very few other people on it. So you can connect this information, at which point now I'm trying to predict whether somebody goes to Microsoft Azure based on pretty much everything else I have observed of that person. And I do this for every single client, for every single event that my client is looking to optimize for. So behind the scenes here is a fully automated system that basically builds predictive models, roughly 3,000 a day, entirely automated in an automated fashion. And that works because the requirements on the quality of these models is not particularly high. I mean, the downside, worst case, I'll show you the wrong ad. That's not a big deal, right? So these models' robustness is more important than in the stock market where you need to tweak out the last 0.05% of performance. Here, that's very different. So we're building these models automatically. And what it's really saying is I'm saying there is a very, very wide feature space, meaning there are many different things that the models look at on the order of, let's say, 100 million different features, columns. Most of them are binary indicators, whether you have been in the past taken a certain action. And then I'm trying to predict some number of positives that I have observed in the past, depending how long the campaign has been going on. And this is kind of the standard representation that now machine learning is being applied to. Techniques here, yes, you could, of course, try deep learning or whatever fancy algorithm. Turns out, in the world of advertising and in this kind of representation, we primarily build logistic regression with all the kinds of bells and whistles that I'm not going to get into, but anybody who wants to know more details, a lot of this work from a technical perspective has been published elsewhere. So, and in the end, what you get is a system that actually doesn't care whether you saw the ad. You find a system that's very good at predicting whether you would have gone to Azure anyway. But as far as I'm concerned, that's okay. Because that's what I'm getting credit for, typically. So we are building the systems that have very high lift in terms of being able to predict certain actions that people take. And you see here a distribution about many different, so certain things you can do very well, and certain things you have a lift very close to 1. So on one extreme is signing up for credit cards. On the other extreme is buying scrapbooking supplies. Which one is which? What do you think is easier to predict? Whether somebody will sign up for a credit card or somebody will buy scrapbooking supplies? Credit card is very hard. Everybody and your grandmother has a credit card. There's no signal, and if 50% of the population have credit cards, lift can't go above 2 anyway, so it's a dud. I mean, it's still very, it doesn't really matter how well you do in absolute terms. You just have to be good enough for the client to be happy. It's a hard problem. Scrapbooking, on the other hand, I mean, apparently there are like on the order of 50 kind of seminal scrapbooking blogs that everybody follows, and once you see one of these blogs in somebody's browsing history, it's pretty obvious that they're into scrapbooking. It's an esoteric hobby where you can find very, very strong kind of signal in the data that we have. So there's a lot more interesting, fun stuff going on in advertising aside from just the core targeting. I will not go into great detail. I do find the question about causality and whether or not we actually care whether the ads influence behavior has been an interesting one that we've been paying attention to. So we did some studies. It turns out there's some really cool work around observational methods that basically use machine learning to allow us to do causal inference without having to run experimentation. Typically, advertisers are somewhat reluctant to spend a lot of money on A/B tests. And so what we did here in this case is to build models that can basically simulate the alternative. So you're having a model that predict for every user what would happen with an ad and what would happen without an ad. And the benefit of that is you can not just say, oh, we drove, I don't know, N% increase in sales. You can actually break it then up into different behavioral patterns and how different types of people are affected by ads. So for instance, in this example here, if you look at people who spend a lot of time in the gym, you see the purple bar, kind of the highest consistently, no matter what the gym was. So it was the self-improvement message. Take a break and come back better. Now, it turns out self-improvement didn't do much for people who like to hang out at fast food restaurants. So the people who spend a lot of time in fast food restaurants, they cared a lot more about the delicious toppings. So you can actually see how this kind of technology gets you very close to being able to predict who has a specific affinity and how that affinity kind of gets translated into being affected by ads. Some other things we can do is, for instance, you can do segmentation. That's something that marketers have been interested in for a very long time. You can do this now in very fine-grained data. This was for some oat milk provider where we looked at that. And then you can find subpopulations, which is kind of similar to what you would get in traditional market studies, except you can now look into very specific behavioral patterns. So for instance, for this one group here who we called the health nut, you see a lot of kind of vegan recipes and certain nutritional interests that describe the activities of these people. Last fun project, and that was more for entertainment. So this is a desk in our office. What you see above is a virtual 3D embedding of the internet. And it's basically every little ball is a part of the internet that in itself contains a number of websites that have certain topics. So you can do these kind of deep learning-based embeddings of people transitions and come up with a view of how the internet looks like with respect to behavioral patterns. I'm happy to share more about this stuff if you're interested. This was really just kind of on the side note. So much about AI in advertising, very specifically from a business perspective. What I care a lot more about these days is what are some of these kind of broader takeaways that you want to be aware of and the gotchas that you want to pay attention to. So one of the things that I kind of term as the models go to where the signal is seems pretty obvious, except that it's not. And it tends to take a lot of digging to really understand what your models are actually doing. And sometimes you're very surprised by what's going on under the hood that is very far from obvious. So let me step back and actually kind of put this into a framework that is relevant far beyond advertising. And that's really this notion of how well can you do. I mean, I used to compete in data mining competitions, and you never quite knew whether spending another 1 week on this would give you 1% benefit or 10 or none whatsoever, right? So there seems to be always some upper bound on how well you can do. And so, for instance, certain things you know you can't do well. The stock market. I mean, it's not a matter of a fancier algorithm. I mean, there is a theory that says if markets are halfway efficient, you know you won't do well. And if you do, you can get very rich, but apparently it's really, really hard to do so. On the other hand, figuring out that this is a cat, I mean, it took us 20 years of kind of creating the technology to finally get to deep learning. So I'm not talking about the fact how difficult it is to actually teach machines to do it, but any 3-year-old is better at this than your favorite financial advisor is at that. So it has nothing to do with the algorithm. It's just some things are easier to predict and some things are harder. Most of what I spent my career on is really kind of in that middle section. It's predicting what people do. Now, it turns out when it comes to people, there's certain things about us that are more predictable than others. So you may have heard of the Facebook study. So for instance, sexual orientation, it's actually not that difficult to predict. If you just know a few things of what people do online, that you can get a pretty high accuracy on. Will I have pizza tonight? I have no clue. It depends whether we hang out too long and what time I get to the airport and how hungry I'm going to be. So the reality is, I don't know. Good luck for a machine to predict whether I will have pizza tonight. So again, certain things about me are easier to tell than others. So what I wanted to show you is what that means for a predictive algorithm and how it behaves in these different scenarios. And in order to do that, I'll walk you through an example to predict who is male. Now that seems to be a really boring problem. Turns out in advertising, you can earn a lot of money if you can predict who is male. Have you ever seen this spot in like your favorite TV show when you're watching on Hulu and you get the same damn kind of pet food thing 20 times in a row? And then you get a little message saying, hey, is this ad relevant to you? And even if you do have 3 dogs, you say no in the vain hope to get anything else at that point. That is because advertising in video is still measured in audience. Meaning every time they're showing this to a middle-aged woman, it counts as a good thing. And so frequency is just not being paid attention to because the incentive is just hitting the right, quote, audience. So that's in terms of demographics, meaning gender and age. So yes, one of the things you make money in video advertising is by predicting who is male. So let's take a look at this. And I'm going to use some Facebook data that was published about 10 years ago with about 200,000 anonymized individuals. So you have this, this is basically up there, the Facebook ID, anonymized. You also have an indicator of self-reported gender. And you also see like an age, like a birth date in there. In addition, you have a number of things that people liked. It's again anonymized, so you have no idea what it is. It just has an identifier. And we are going to use logistic regression, but I don't think it matters really in terms of what the technology you want to bring to bear on this. So let's actually try to predict the gender just based on age. How well do you think I'm going to do? Are we having a stock market here or a cat? Stock market, cat, any opinion? I shouldn't be able to predict gender based on age. At least usually I shouldn't, with a little bit of caveats to it. So it turns out it's one of these examples where you don't have much signal. The overall accuracy is 60%. Well, there were 40% men, so that shouldn't surprise anybody at this point. The AUC, which is a ranking measure where 50% is random and 100% is deterministic, meaning perfect, we are at 58%, which is not particularly impressive, though if this was predicting stock returns, you would be rich owning a beautiful island in the middle of nowhere. So, you know, don't. But this is the interesting part. This is, on the holdout set, the predicted probabilities. So I'm looking here at the distribution of the predictions. Now, how is this being used? If you were to actually target people, you're really just interested in the highest prediction. This is a very common use today of AI. You let the AI rank things by interest to you. You let it rank by relevance. You find the most, I don't know what, like most likely people to click, most likely. So there is a large number of applications where we only care about the top of a ranking as provided by a machine learning algorithm. So in this case, if we just look at the top 1%, it's actually not that terrible. In the top 1% prediction, you get 75% men. So let's move on and add all of the, quote, likes to it. So now I'm not adding rows, right? I'm not increasing the training set. I'm adding columns. I'm adding additional information to the problem. I'm getting the model, giving the model more kind of features to learn from. So what do you think is going to happen now? The accuracy is actually lower than I assumed it would be. The AUC is 92%. That's quite impressive. But what I really wanted to show you is this. Now, that's a very opinionated model. This model knows that it knows something because it will predict either almost 100%, I mean probability of 1 for being male, or 0. So it has basically moved from what started out as a more or less normal indecisive into these two very pronounced peaks. And not surprising, if you now just look at the top 1%, all of them are male. What about those people where the model is still kind of clueless and can't make up its mind? Who are those people? Come on, at least one guess. New users? So it depends what audience you talk to. If you ask this question to a marketing gang, you get shared accounts or then maybe some kind of gender fluidity arguments. It's people without likes, which is probably what you meant by new users. So it's still people where the model doesn't know what to do because there's no information. But that's already kind of a hint of where I'm going with that, because you have some people where you have a lot of information. Those will be in the extreme. And then you have some people where you have very little information, and they will be in the middle. So just to kind of share with you the progression is, as you go through the additional information, a model that started out having almost a normal distribution for the predicted probabilities gets more and more pushing towards the outside of the distribution, and then ultimately develops these two spikes as I'm adding more features. So I'm adding 10, 100, 1,000, 10,000, 100,000. Why do I explain all of this? What does this matter? Because almost every problem I've looked at, almost problem you will ever look at if you do this for a living, it's really a little bit of both going on. You rarely ever are living in one of these two extremes. You often have combinations of them where, okay, maybe not cats in the stock market, but I mean, my point being that some part of the story has a lot of signal and others doesn't. And what then happens is your model is very happy to just focus on where the signal is, and you are not seeing all of those cases where there is less information. Now, I'll give you a few examples throughout this, and the first one is the first time I really consciously encountered this problem is when all of a sudden the median lift across many different campaigns doubled. Now, you could think this is good news, but here's the thing. I mean, there's no reason why people all of a sudden lose their free will and become very predictable. There's no good explanation why things should get a lot better if I hadn't done anything. So when we tried to understand what was going on, we actually looked at those very predictive websites. And there, for instance, women's health space was very indicative of people being interested in luxury cars, software products, credit cards, buying pizza, and staying in hotels. And there were a whole bunch of websites like that. And most of them, I'd be very curious if anybody here ever saw any of those before. So what's going on here? Well, let's take a look at what kind of the underlying, like how people use those websites and how they go from one to the other. So I'll show you a graph where a red point is a host name, and there's a connection if 50% of cookies going to one also show up in the other host name. So it's kind of an overlap of audience, if you want. This is what it looks like in an early instance, and down here you can take a look. This is actually a website or websites related to traveling to Boston. So it's news about Boston and search around Boston, and it makes sense that this is what people do or what kind of technical integration there might be. However, what about this? This is where my friend Women's Health Base is. There's a lot of activity going on, and I would also like to point out the very diverse hobbies. China on TV, wrestling news, and other ill-spelled stuff. I can't imagine any person doing that. There's just no way. What you see here is basically a footprint of a non-human activity / fraudulent bot network. These are not people. This is something else that somebody has written code for to do. Now, what has this to do with my predictability problem? Because bots have always been in the internet. So what's going on here? Well, what the owner of the bot network realized is that in order to monetize your bot, it's much smarter if you make your bot do all the things that marketers love people to do, like going to the homepage of the brand. So now what happens is that the bot first visits, say, Guthy-Renker, and therefore the value in these auctions goes up by almost a factor of 10, because that's retargeting. I'm sure you look at the pair of shoes, and then the pair of shoes follows you around for the next 3 weeks, wherever you go on the internet. Yes, so this is retargeting, doesn't require any AI or machine learning or anything. It's just, there's a lot of money in retargeting. So the value of a cookie that has been at one of these sites before goes up, meaning now the bid prices go up, meaning whoever owns the bot makes a lot more money on those websites that were also created just to have bots visit them. Give you a sense of the scale of the problem, we measured kind of the bot traffic on various conversion events that we're predicting, and yeah, so the winner was the Clorox video completion pixel. I mean, yes, if you think about it, it's, only bots are patient enough to sit through all of these Clorox videos. So if you start predicting who will actually watch the video to the end instead of skipping, you end up only having bots in that population. So that's an example of what I was talking about, where you have two populations. You have, on the one hand side, people, and then you also have bots. And it turns out that on that spectrum, people are unpredictable. Bots, on the other hand, that were created for the sole purpose of taking exactly that action that the market is interested in, they have these very high scores from the model because there's where all of the signal is. So when you now start targeting your top 1%, you end up only targeting bots. Now, once we kind of wrote a bot filter, that's when my performance went back down, and for once we were actually quite happy for performance of our machine learning models to decrease. So I know we started late, and I know that you all want to go home at some point. I can entertain you with advertising stories for a while. I will skip to. Okay, not very decisive. Fine. Well, you have to drag me off here. It's as simple as that. What about clicks? Okay, who here recently clicked on an ad? Okay, let me rephrase. Who recently had something popping up on their screen, realizing they must have accidentally clicked on an ad? My point. So here's the thing. I mean, clicks may be viewed from the advertisers as an expression of intent, but guess what? More often than not, it's an accident. Now, it may be an accident from our perspective, but it's not an accident for the AI that learns to predict clicks. Because the accidents are, in fact, quite predictable. In fact, they are a lot more predictable than the intentional clicks. And basically, what happens if you predict and you optimize towards click-through rate, you really only reach people who are for sure not interested in your product. Let me show you evidence. One of the things you see is, if you look at models that predict clicks, they don't care who you are. They don't care what you're interested in. They only care of whether you're right now on the flashlight app fumbling in the dark. So the context of what you are doing at a certain moment is very predictive of the probability that you will accidentally click on an ad. And you also see then when you do click optimization, things like that. Can you tell me how to get rid of this ad? Yeah, it's this little box that has almost the same color as the background, and it's half below the fold, like the end of my screen. So yeah, chances of accidentally clicking there is much higher because the trying to get rid of it is kind of disappearing. So this is what you get when you then optimize towards clicks. You get more accidents. I will skip the luxury car example, and I will instead show you an example of predicting who will go to. You can look at the slides if you want to. One of the things people in advertising, like an audience people love to advertise to, are frequent travelers. A, they probably have a job that pays well. B, they probably have a bad conscience being away from home with the family waiting, so they bring home gifts. So as far as advertising them stuff, that's an excellent audience to reach. Now, where do you find frequent travelers? At airports. So how about I'm trying to predict who will show up in an airport? So here we're actually literally predicting who will show up at the physical JFK location based on their browsing history. And here's the model. So these are the top 40 highest scoring URLs, indicating that you will go to the airport. Okay, let me try to enlighten you. So, okay, this is something in Spanish. Seems to be religious content. Those websites, that's a little bit more telling. Jump seat news. And then we have a whole bunch of NFL fans And you also see, and I just let the data speak for itself. So, yes, you can predict who will go to JFK, but chances are it's a lot easier to predict the people who work there than the elusive frequent traveler. Now, you didn't think about that when you told me that I should look for frequent travelers at the airport. And that's part of the problem. When you are pointing an AI onto a certain objective, you want to think really hard if this is really what you want. Because they are damn good at finding any weakness and exploiting it, and you may not understand your model sufficiently to ensure that this is really what you wanted. And this is really the discussion for which I wanted to have some more time. My last example is not from the world of advertising, but kind of a more concerning one, where we looked at a medical application where we're trying to identify in images whether or not there is breast cancer in mammography images. So basically, you have medical equipment that takes these images, and then there you can identify candidate regions, and you're trying to kind of have an assistant tool that can diagnose cancer. We had a data set provided, and we built a model that ended up being extremely accurate. So it was far better than we had expected, relatively speaking, and we were kind of quite proud of this until, and I'm happy to share kind of the accidental story of how this happened, but we eventually looked at this plot where you see on the x-axis the patient identifier on a log scale, and on the y-axis you have some model score. Anything strikes you as interesting here?
Empty gaps.
Huh. What happened to those people? Like, where are all the patients that were supposed to be in between? It gets more interesting if I now color the different points based on whether or not they had cancer. What you see now is that patient ID is, in fact, the most predictive feature in identifying who has cancer. Now, obviously, we did not include the patient ID in the model, but you can show that doing so will improve the model further. What's going on here? Chances are somebody heard that in order to build good predictive models, you need a lot of data, and getting a lot of data, they pooled information from different locations, different hospitals. One of them may have been a treatment facility, one was a screening facility. So the patient ID is really just a proxy for the location. Now, what does this mean? Should you include the patient ID in the model? Yes? Show of hands? No? Show of hands? Okay, let me ask differently. Should the model know which hospital you are in? Yeah. Oh, okay. So, if you don't include the patient ID, what the model had learned, and the reason it was doing very well, because it basically had learned the average grayscale. It still figured out which hospital you were in, because these machines have different calibrations, because big machines, different calibration. So even if you don't include the patient ID, the model picks it up, kind of halfway a little bit. But clearly, you should have known about all of that. The hospital should be included in your data set to start with. Now, let me ask this. Where would you be comfortable using this model? Not at all? Maybe? So if you use it in one of the 4 locations and you actually include an indicator of location, I'm quite comfortable with the model. I think it's fine. Can you use it in any other location? Probably not, except I would still feel that you primarily have a base rate problem, meaning your probabilities are not calibrated, but your ranking in terms of the most likely cases may still be somewhat useful. understanding the implication of what happened in the data collection process on the reliability of your model, the fact that it looks far better than it really is because the test set has exactly the same, quote, sampling problem of having come from these 4 locations. This is all part of what I call the secret life of your model. And ultimately, what happened here is, again, this signature that certain things are making their way into the model. You didn't want it to, but it turns out that the location kind of bled as very strong signal, far more so than the kind of indication of cancer. So stepping away from this particular instance, what is the bigger picture? Number one is that understanding what models do is hard. There is this notion of the model zooming in on information, and it's hard for us to understand where it came from. And I personally am not convinced that transparency is the silver bullet. If you think about what happened in that breast cancer model, no amount of transparency on that model would have ever told you that there was a problem with different locations. It was sheer accident, kind of like a lucky accident that we've merged the data set and looked at it in terms of the patient ID, which was initially not even part of the image. One thing that's important to consider in the discussion of transparency is, and that goes back further to the kind of example of the frequent traveler, there's a huge difference between transparency of the model and understanding what it does, and transparency on how a prediction became to be what it is. I personally challenge, I don't think we will ever be able to really understand models. There's a clear trade-off between building good machine learning models and what the human mind can comprehend. I mean, that's why we built them, right? If we could think in, I don't know, 5,000 dimensions, then yeah, sure, we wouldn't need models, but we can't. There is an explicit trade-off, and you pay a price for understanding something, and that price is accuracy or performance. Understanding a prediction, however, is slightly easier, because there you can basically very deliberately parts of the input to see, well, if you change the gender of the kind of applicant, does that change the predicted kind of suitability for the job? So for predictions, you do have some abilities to poke the model to understand what it might be doing underneath. But the key component to all of this is a very deep thought process around the data. It's not just the model. All of the cases I told you, it really came back to the data having certain properties. You can't just diagnose the model if you care to understand the model. The second discussion that is very important to have, and we have a lot of that right now, is talking about biases. And the primary concern is, well, if your training data is biased, then so will be the model. And that's correct. But 2 points here. Number one, that doesn't mean that people are any better at this. In relationship between human decision-making and models, at least we know how to fix models when it comes to fixing the training data. I think making people and their decisions less biased is a taller order and an important conversation to have. Now, the formal definition of bias is actually very difficult, and people pick whatever they feel like a bias they don't like, and then they show that the model is bad at it. Turns out that there are many different ways of defining bias, and many of them are mutually exclusive. So finding a model that is unbiased across all of these different ways you can define bias is in fact impossible. The reason I'm saying that unbiasing your data set isn't sufficient, if you listened very carefully to what I said, I basically told you that models are very good at creating biases out of unbiased data sets. It will always favor the ones with more signal. It will favor whoever has more information. The more extreme predictions will always come from instances that somehow had more signal. And so one final example and I'll show you this in the experiment on the data set here, is I'm going to predict taking a certain action, but I will make sure that gender is unbiased. So I'm going to look to predict certain people liking certain things. That's what I'm predicting. And I'm going to see that they are not very biased. And what you see here is if you just rank based on the predicted probability of taking a certain action, initially this model basically didn't identify any female as being likely to take this action. So you have a very strong gender bias on something that originally almost had an even gender class in the positives. And so the responsibility for biases still rests with both the people who use the model and the one who created. And just simply testing or enforcing an unbiased training set, as I did here, is not sufficient to avoid these kind of information-induced second-order effects that can still lead to all of the top 10 being strictly one gender. So if you want to have both genders equally represented as applicants for a job, well, then you have to invite equal number of male and female. You cannot delegate the responsibility of fairness to AI. This is simply not a fair requirement on algorithms and tools. We as decision makers still have the responsibility for the action we take. And this with plenty of overtime, I'm at the end of my talk. Thank you very much.
Great talk, really interesting. I was curious about the point of transparency you mentioned at the end. So what if you use like some class activation map or like food map to like superimpose some kind of a heat map onto the breast cancer scans? Would something like that be sufficient to then highlight the erroneous version? It wouldn't show the hospital problem, but could it be enough to just show you, oh, the model is doing something average here?
So if really the model found something that kind of the average grayscale is in a certain range and therefore it's cancer, I have a hard time imagining and first off, initially this is like, we're not really having the images. What we do have is a 117 numeric description of the images. There was some pre-processing done. So you didn't even have the images. It was processed. There was a lot of intellectual property involved in that thing. So I really don't see any way of finding that particular instance. I really don't know. I think in general, you're absolutely right. Like any technique you have for dissecting, but it's again looking at prediction patterns, right? So I like to understand models through understanding what predictions they make. So the more tools we have, none of them can clearly refute the hypothesis that there is still bias left.
In the context of your ad exchange slides, I just need to understand, you said you were looking at IP address of the Wi-Fi which they're using to identify the entity. My question is, there could be many people using the same Wi-Fi, right? So
Totally.
How do you distinguish between among those people?
So what actually happens there is basically kind of a TF-IDF way. You can either look at this as PageRank or as a TF-IDF where you're saying you downweigh IP addresses where you see many different devices on. So they get a very low connectivity score, and you upweigh, so it's kind of an inverse based on the number of different devices. So you will say two devices are probabilistically related if they connect through IP addresses that have a high weight, which means very few other devices are there. So I skimmed over the actual logic of, it's not as simple as I showed it in the slide. There is some kind of a network analysis tool behind the scenes on that one. By the way, I'm never sure I get it right. I mean, your neighbor could have hacked into your Wi-Fi, right? I mean, but again, we're talking advertising here, right? So, you know. I mean, your neighbor might like your new car and buy one too.
Can you expand a little bit more on causal inference without experimentation?
Okay. Yeah, so basically the typical problem in causation is that you have confounding, especially if you do targeting. So if you just look at the people I show an ad to, of course they convert at a higher rate because that's why I showed them an ad, because that's what I predicted. So what you need to do is kind of control for that confounding, and what is not working is propensity matching a la Nielsen. The reason is that I have better data. I can create more extreme probabilities that they can't actually match. So you will always have remnant kind of targeting, pretending to be causality. Now, what happens here is, and we have published that, so I'm happy to share that, it's basically one of these double robust estimators out of the Berkeley group that does stats where you build two models, one that predicts who you will target, one that predicts then the probability of conversion given targeting. And I think the theory of double robust means as long as one of those is a consistent estimator, you can actually estimate the causal effect. We did a test in that paper where we compare it to an actual A/B test, and that came within 5% on the causal effect. And that seemed to me, I mean, the irony is I can only measure myself. It becomes an incentive problem in the sense that I'm the only one who can recreate correctly the probability of exposure because I have my own propensity model that I used. So I can measure my own causal impact, but you can't have an independent third party like Nielsen measure me because they cannot recreate that confounder correctly. So in the end, we build a kind of free causal estimating tool, and then I get phone calls from the salespeople, hey, can you run this again? And I said, yep, I can, but you have looked at the creative, right? That thing is not going to move anybody. So there, I mean, we had a hard time selling it, both because we are not independent of ourselves in terms of estimating it, and B, because marketers, when their ads don't work, often don't want to know. But, okay, so.
Well, let's thank Claudia again.